CEDAR Wednesday. I don't know about you, but it feels like Friday. No, I'm kidding. We have another exciting day of talks, interactions, and poster presentations today. First, one announcement. Today at noon, from 12 to 12:45, we'll have a town hall here in this room on decadal survey and future of CEDAR instrumentation. Since this affects, well, at least all of us, I would urge you to all stay here and talk, interact with all of us, and hopefully we can put some interesting, compelling papers for the decadal survey. So this morning we have 4 talks. The first will be given by Ercha. That is an early career highlight, 3D ionospheric imaging and SED reconstruction with a new TEC-based ionospheric data assimilation system, or TIDAS. Ercha?
All right, good morning, everyone. Thank you for providing me this opportunity to talk about my recent studies. So this is a presentation talking about 3D-dimensional ionosphere imaging and storm-enhanced density reconstruction. So the storm-enhanced density, the SED, is a highly structured ionospheric storm-time features. It refers to a large-scale TEC and electron density enhancement along a westward, sunward, poleward channel that's usually observed in the local afternoon and dusk sectors at mid-latitudes and subaurora latitudes. So it is a very important density gradient structures in the mid-latitudes and are widely investigated by using 2-dimensional GNSS TC results. However, its 3-dimensional structures, especially the altitudinal information, remains insufficient. Therefore, in this project, we constructed a TEC-based ionospheric data assimilation system, the TIDAS. We aim to provide the 3-dimensional ionosphere imaging and reconstruction of the 3-dimensional structures of the storm-enhanced density. However, as we know that accurately imaging and modeling the ionosphere has always been a challenging to our space weather community because the ionosphere is a highly dynamic entity that's subject to very severe space weather fluctuations, both in space and time. So because of this, we're going to be using the ionosphere data simulation. It's a useful technique to provide a valid ionosphere specification by ingesting various data sets into a background model so we can get an optimal state estimation. So it has been proved as an effective technique to overcome the limitation of the unbalanced distribution of the data set and to improve the accuracy of the background model so that we can get an optimal state estimation. So as you can see that we already have a lot of great data simulation products. Some of them are using theoretical background models, such as the global assimilation of ionosphere model, the game developed by Utah State University. And we also have the game developed by the JPL, University of Southern California. And some other models, they are using the coupled ionosphere-thermosphere background model, such as the TIGCM and DART, combine them together. And some of the models, they are using the empirical background models because they have the very low computation cost. So such as the IDA 3D, IDA 40, Global Ionosphere Specification, IR10, MIDAS, as well as a lot of IRI-based data simulation products. So these have the merits to provide a global scale specification of the ionosphere. However, we still have some needs. So among all those needs, I would like to point out we have the R2O research to operational needs. Yeah, we need to provide operational space weather forecast and nowcast. And another thing is most of the data simulation products have been built to run on a global scale. So they may not always have optimal performance to represent the regional structures. So we also need to provide a regional high-resolution, high-fidelity mesoscale structures by using data assimilation technique. So speaking of the operational and regional products, we know there are lots of great products, such as the US total electron content, the North American TEC that provided by NOAA's WAPC, and they recently extended into a global GloTech data simulation products. And we also have some other regional data simulation products, such as from the European sector, the Australia and the East Asian sectors. So these are great data simulation products. They provide quasi real-time operational products of the two-dimensional total electron content. So in this project, we're going to move a step forward to provide a regional, high-resolution, but three-dimensional electron density data simulation products. So we aim to address the mesoscale structures, especially the storm-enhanced density in the mid-latitudes. So that's our science project. That's our science object. Okay, so we call it a TEC-based ionospheric data simulation system. We call it TIDAS. So we focus on the North American sector, not only because we have reported a very significant SED plume here that due to very complicated dynamic electrodynamic processes, but also due to the availability of the dense network of ground-based GNSS receivers over this region. So we're going to use the data. Oh, sorry. Here. So the first one is the line of sight TEC profiles from the over 2,000 GNSS receivers, and we also use the cosmic radio occultation electron density profiles. And the third one, we use the JSON TEC above the ocean. And last but not least, we have the Millstone Hill ISR measurement that provides altitude resolved measurement of the electron density profiles. So we combine them together. And the background model, we use the NE-Quick model. It's a very quick run model that provides electron density profiles and integrated total electron content along any given vertical or slant path. So one important question in data simulation is how do we provide a reliable specification of the background error covariance matrix? Because that's a key point. That's a key parameter that directly influences the weights of the background model and the performance of the data simulation. So in many prior studies, this background error covariance matrix are usually expressed as a function of ionosphere correlation length. They are expressed in the form of elliptical Gaussian-like distribution, such as these two. So these are horizontal ionosphere correlation length, and this is the vertical ionosphere correlation length. So they are expressed as an elliptical Gaussian distribution. However, in reality, especially during the space weather events, the ionosphere correlation length can be more complicated, and the background covariance matrix can be even complicated. So in this way, we use the ensemble-based algorithm. So this is widely adopted in theoretical-based data simulation, such as the TIGCM and the DART. We are using the ensemble output of the model. By perturbing the model inputs, providing the ensemble, we can calculate a better background error covariance matrix. So here we perturbed the NE-Quick model to provide a corrected ensemble of the NE-Quick, and we calculated this background error covariance. That's the bottom two panels. We can see they are largely different from the top two panels. They are more anisotropic, and they have more complicated mesoscale structures. So they represent more a reality-based background covariance matrix. So that's ensemble-based algorithm. And we also use three-dimensional variation method and sparse matrix storage. To save the time, I'm going to skip this mathematical description. You can meet me offline to talk about this further. So now I'm going to show you the results. So that's the three-dimensional regional electron density specification So a key point is that we have very high resolution for this product. It's 1 degree in latitude, 1 degree longitude, 20 kilometers in altitude, and 5 minutes temporal resolution. So this is the reconstructed three-dimensional electron density. So that's the longitude, latitude distribution at different altitude. So this one is the latitude, altitude slice. So we can see the stormy enhanced density plume structure are clearly reproduced, reconstructed as this poleward, sunward elongated high density channel. And in this top mid panel, we show the shaded contour of the NMF2 and HMF2, the peak height. So this is the peak height, HMF2, and this color-coded region is the NMF2. So we can see this enhanced density structure, the ridge-like structure that represents the format of the SED plume. We know that it's about 40 to 60 kilometers higher than their adjacent poleward and equatorward counterparts, and they are 30 to 50% density larger than the adjacent regions. And this animation, we can clearly see these ridge-like structures showing in this region. So this animation here is also the HMF2 and the MF2, so that's the color bar. And this right globe, this is the total electron content. So we provide high resolution variation of the data assimilation products. So let's take a look at the SED plume again. There you go, around this region, ridge-like high density extended poleward sunward. So our TIDAS data simulation results represent very well the SED morphology in three-dimensional structures. So we did some preliminary validation. So the first one we're using, sorry. So the first one, we use the pre-excluded TEC data. So we can see before the simulation, that's after the simulation, we can see this more center-based and with narrow distribution. And so this one, we're using the cosmic profile to conduct an internal validation. By including and excluding the cosmic profile, we check the assimilation results. And that's the reconstructed electron density maps at 300 kilometers at 3 different universal time. So that's the cosmic profiles. So we can see the data simulation agree with the cosmic profile relatively well. And we're also using independent validation. Here we show the ionosphere variation, the electron density profiles from 5 different stations. You can see here. So we can see the background NE-quick model that's merely grabbed the general diurnal variation of the electron density profile without clear difference in the quiet day and the storm day. However, the TIDAS data simulation results provide very well representation of the storm day enhancement of the SED plume. So to the right panel, we show the another internal validation by using our Millstone-Hill ISR measurement. So that's the electron density profiles. We can see the data simulation results agree very well, and the graphs capture the SED structures with very large F2 layer elevation and enhancement in the F region and the topside ionosphere. So in general, they provide a relatively well representation of the SED plume. So as a summary, we built a new regional TEC-based ionosphere data simulation system, and we provide a high resolution, 1 degree by 1 degree by 20 kilometers by 5 minutes high resolution regional data simulation products to represent the mid-latitude density gradient structures. So in the future work, we're gonna keep testing this model. By improve the model accuracy, we're gonna including the ionosphere data sets, and we can also test its forecasting ability in the future. So if you have more questions, you can feel welcome to check this recent publication about this paper. Thank you.
Question for Ercha?
Oh, tomography.
Yeah.
Okay,
How
okay.
did you invert the TC? It's using tomography, right?
It's kind of similar but sort of different data simulation. So we provide its ensemble 3D variation method. So it's a combined ensemble based to calculate the background error covariance and using the 3D variational methods to do the optimal state estimation. So tomography is another method to estimate the background electron density, and some other people, they using tomography methods to estimate it.
Yeah, I couldn't resist trying to do instant science with your data, which we were just doing to try to demonstrate the technique, but let me ask you whether these two things I saw seem real. One is that the SED plume seemed much narrower than I sort of remember, and I find that would be really interesting if that's generally true. At the same time, when you look at the SED plume, on the northeast side, everything was very dark. But when I went to the southwest side of the plume, there was a lot of light white. Yeah, in the previous slide there, or either one. But it looked like there was a lot in the previous slide that you showed. Looked like there was a lot more. Whoops, the other direction. The one you showed. Just go for it, back. Go one more. Where you were. Yeah, that's good. Oops, that was perfect.
This one?
Okay, that's good. That's good. Look at the plume. You have the deep blue on the right, and you have the light white to the left, all to the left of the plume. As though there's a fundamental difference between the physics of the polar cap on the right side of your plume versus the left side of the plume in terms of the densities that are getting into the polar cap, as though the plume is not just a flow channel, but it's separating two different fundamental aspects of the polar cap that I have no idea what that means, but it looks really interesting.
Yes, I agree with you. So this very large density gradient structures, not only the SED plume, but also to the right side, we saw this dark region. That's the kind of trough region, mid-latitude trough. So they have very low, dark density structures. And then to the light, we can also see there's a EIA region, and there's a very large. There are some mesoscale structures, the small-scale irregularities that are embedded within the plume and adjacent regions due to the gradient drift instabilities. So because of we have this high-resolution products, we can reconstruct these structures. So this is afternoon. Yeah, dusk time, yeah.
So in the interest of time, we are going to keep moving. Thank you once again, Ercha. And the next we have is Grand Challenge tutorial by Yue Deng, Qingyu Zhu, and Astrid Maute.
First, thanks CEDAR Science Steering Committee for selecting our Grand Challenge proposal. It's a big pleasure for us to present and give the tutorial about the interhemispheric asymmetry in the IT system. I will start the tutorial, then our co-convener Qingyu and Astrid will follow up with details with different focus in different area. Right, symmetry. Then what is symmetry? In the everyday language, symmetry pretty much indicates something imbalance, something harmonia. And in the mathematical language, it refers to some variable is invariant after certain transformation, such as refraction or rotation. And it's not difficult to find an example of symmetry in our life. Just look at yourself in the mirror or look at the people sitting next to you. But don't stare. That's not polite. Believe it or not, actually, statistic shows only 2% of the world population has true facial symmetry. I'm not exactly sure what the definition of true facial symmetry, but anyway, there has to be something there. if you are a normal human being like me, so 98%, you probably have something asymmetric. So, well, this just to show example, this, oh, I'm sorry. This is probably a more like perfect or true facial symmetry. This is like a little bit less symmetry. And somebody may wonder, oh, does it make me more attractive or not? Well, that's a question probably to artists, not to the scientists like us. And the bottom line is, asymmetry is popular, normal, and much more common than symmetry. And the same case for our, for upper atmosphere, the science domain. I'll try to start some general question. What causes interhemispheric asymmetry, and what's the format of asymmetry in the parameters we are interested? And in terms of cause, actually, the ionosphere-thermosphere asymmetry can due to a lot of different processes, including internal processes or some processes stemming from the solar wind magnetosphere coupling. And again, show you a couple of examples. First of all is a geomagnetic field. Our Earth's magnetic field is not a perfect dipole. And we are here shows several possible configurations of the magnetic field configuration. First is a perfect dipole, and the second is a tilde dipole, and third is a shift to the day side and shift to northern hemisphere, and the last one is the shift to the day side. And the reality is our Earth's magnetic field is tilde and shifted dipole. So naturally, it's going to generate a lot of asymmetry in our system. And seasonal variation. I don't know if everybody pay attention or not. Yes, actually, yesterday is a summer solstice. So, which means our northern hemisphere got way more solar irradiation than the southern hemisphere, which is going to drive a lot of asymmetry again in our IT system. Another one is the process actually comes from the solar wind magnetosphere interaction, and it will cause a lot of asymmetry in the high latitude convection pattern and the auroral precipitation as well. Meanwhile, due to the topography asymmetry and also the atmosphere dynamic asymmetry in the low atmosphere, the atmospheric waves propagating to the upper atmosphere could show strong asymmetry as well, including gravity wave, tides, and planetary waves. All right? A lot of things can drive asymmetry, and actually the observations has revealed the symmetry manifested in different forms. I just show you a couple of examples. I'm not going to be comprehensive, indeed. If I miss something, especially your favorite one, well, you can blame on me. Don't get too mad. All right? So here I'm going to show example in the high latitude forcing, including both aurora and Poynting flux. The top left panel shows simultaneous observations of aurora from two satellites. One, imaging from the northern hemisphere, one from southern hemisphere. Clearly, the aurora structure and the polar cap are quite different. And why? But this is just one snapshot. Then we look at the asymmetry in a very different time frame and in a different way. So this axis is day of year. So look at the variation during the whole year. And the parameter we look at is hemisphere power, which typically represent the total particle flux in the whole polar region, and is calculated based on the NOAA satellite. The top panel shows the hemisphere power in both northern and southern hemisphere, solid line, northern hemisphere, dash, southern hemisphere, and the bottom line shows the difference. The difference can be negative and positive, but in general and averagely speaking, the northern hemisphere is 5 to 10% higher than that in southern hemisphere. And then we look at, when we say where, basically it's not me or even not my team, I say, our community, okay? And look at the Poynting flux estimated from the DMSP satellite, which also show a strong asymmetry. In, I think this is during some certain season, and if you look at the conjugated beams, the northern hemisphere Poynting flux is 25% higher than that the southern hemisphere, if you calculate the total number. And if you look at the distribution, actually they have a different distribution as well. So definitely more detailed study about the reason and in different time frame as well is needed. Then we look at the asymmetry in thermosphere. If you look at the neutral density during a whole year observed by CHAMP satellite, I think the 6 years has been studied. Then look at the 6-year average. By the way, this is a neutral density variation. So the annual average has been subtracted. If you look at those annual variation in both hemispheres, the southern hemisphere more or less show a clear annual variation, but the northern hemisphere more indicated a semi-annual variation. Why? What's the mechanism? I'm not sure I can answer this question. Then we compared the neutral wind from conjugated FIREBIRD interferometer stations. And again, the neutral wind in both meridional and zonal direction show asymmetry in different seasons as well. Meanwhile, the gauge opportunity ratio observations, GUVI opportunity ratio from the timeless satellite showed a strong asymmetry in the thermosphere composition, and this asymmetry became much clearer during a storm time. There's a big decreasing in the southern hemisphere, which is way more than northern hemisphere. In the ionosphere, the asymmetry also is quite evident. So this basically shows the TC at a room local time, variation along the latitude. And the left panel shows the variation in geographical latitude, and this variation shows a geomagnetical latitude. And the solid line is for December, and the dashed line is for June. And this figure basically indicates two things. First of all, there's a strong annual asymmetry. So in December, almost everywhere, the TC is higher than the summer, June. Meanwhile, if you look at if you compare the TC along the equator, no matter it's geographical equator or geomagnetical equator, you will see the asymmetry there as well. And how can we explain that? Another thing is tides and tides, traveling atmospheric disturbance and traveling ionospheric disturbance, tides, can be quite asymmetry in many different ways. First of all, the magnitude could be asymmetry, and also propagating speed and time could show asymmetry as well. So those asymmetry could be due to multiple reasons. First, the energy input in the high latitude may not happen at the same time, and also the intensity of the energy input could be different as well. And meanwhile, when propagating to the middle low latitude, the background ionosphere-thermosphere condition could be different. And this asymmetry of tides and tides can cause a lot of variation or asymmetry in the ionosphere-thermosphere in the low and mid latitudes. I think Qingyu is going to talk about more that. in his part. All right, I'm sorry. Okay, why? Why should we? Why we're here? Why should we study the asymmetry? Well, this topic actually has been acknowledged a lot by the community, but we don't think we really have sufficient understanding. Oh, I'm sorry. Sufficient understanding of this topic. Oh, I cannot go. Okay. Of the nature of the interhemispheric asymmetry yet. For example, let's keep progressing. The asymmetry has been typically ignored in the data analysis, and we typically combine the observation from two hemispheres, since the data coverage is limited. Then based on that data set, we created an empirical model, such like Weimar. That's a typical approach to when we have a limited data. And if we start from those empirical model and use this model to drive other physics model like GCM, then the lack of asymmetry input to the GCM model has prevented the simulations from those models to test the impact of the asymmetry on the IT system. Basically, if you don't have asymmetric forcing, how could you expect your simulation will present the asymmetry in the IT system accurately? That's no way we can do, right? So therefore, this workshop will focus on the quantifying the interhemispheric asymmetry difference observed in the IT system and understanding their cause. Cause could from above, could from below, and the importance for our up atmosphere. And this topic is timely since it will leverage several efforts, including both simulation and observation in our community. First is CubeSats Drive Science Center, phase 1, NASA Drive Science Center, unfortunately, didn't get selected for phase 2, but it created a very nice platform and built up a nice sub-community to focus on this topic. And the goal of this center is to generate a next generation modeling and capability to account for this asymmetry. And their approach is to start from observation, then to uncover the model shortcoming, and then use the improved model to complete the observational-based understanding of the MIT system. I would like to show a couple quick highlights from the effort of those teams. First is the magnetic field configuration impact on the particle precipitation. And this work was done by Mei-Ching Falk at NASA Goddard. She replaced the pure dipole, the perfect dipole magnetic field, with the IGRF. Then look at the particle precipitation in both hemispheres. The clear asymmetry can be identified now. So the right panel basically shows the effort through collaboration between Alex Glosser from Goddard again and people in my team to study the neutral dynamo effect on the polar cap potential. So this left panel shows the potential driven by the magnetosphere only, but the right panel shows the potential driven by magnetosphere and the neutral dynamo. So the difference is quite evident, and the magnitude distribution, everything got changed. So this indicates during a solstice, usually winter solstice, summer solstice, the neutral dynamics could be quite different in both hemispheres, which may feed back to the magnetosphere and created or contributed to the interhemispheric asymmetry in the polar cap potential as well. All right, and the improvement in the ground-based observation in the last decade strongly enhanced our capability to study the interhemispheric asymmetry. For example, the super-down radar have very nice coverage for both, high latitude and polar cap region, and we can definitely do some interhemispheric study using the super-down radar. And meanwhile, the GNSS-TC utilizes more than 6,000 global receivers to cover most of the land area. Well, the coverage is not ideal, we know that, but during certain longitude or certain domain, the interhemispheric asymmetry definitely can be studied as well. Not mention about the recently launched several satellites, including Icon Gold and Cosmic 2. I had a lot of talks in this CEDAR workshop already about how to use those data to study the asymmetry. And, sorry. Okay, maybe, okay. And meanwhile, the future mission, GDC, probably you have heard about that, the Global Dynamics Constellation mission has a very important objective, is to determine how hemispheric asymmetries in the Earth magnetic field, season variation, and magnetosphere input affect the IT system. That's exactly the goal of our session. So maybe our session can help to the mission preparation. Our session will only last 3 years, and this mission will launch in 7 years. So probably it's difficult to have a really overlapping or use this data, but we can help in terms of mission preparation. We have a bunch of questions here, proposed challenging questions. And our overarching goal, of course, is to understand the asymmetry in the forcing from both above and below, and to investigate the impact on the IT system. And we have specific questions we'd like to address, like what's the difficulty, and what condition that asymmetry happen more often, and what's the spatial temporal features, and how big is the asymmetry from magnetosphere forcing, and how big is from the atmospheric forcing, and what's the relative importance of those different forcings? That's a big question. And specifically for the first year, we would like to start with those short list of questions. And first, what the recent results and the resources are available to address the questions? And I list several of them, but no means I try to be complete. We're open to suggestion. I know people have fantastic ideas. Feel free to talk to us or provide us suggestion. And what are the hurdles for making progress? And what's the problem can we realistically push forward over the next 3 years? We don't have an infinite amount of time. This is only the 3-year challenging session. Is anything we can do in a short time term, like 3 years time frame? And can we identify ways to characterize or parameterize the asymmetry or interhemispheric asymmetry in forcing and IT system? So we have the interhemispheric asymmetry index, which basically is a difference over the average between those two hemispheres. Well, this is just one way to show the asymmetry. And certainly there are more ways to do that. The asymmetry index probably will practical for point-to-point comparison. How about 2D comparison? You have a 2D map. You want to see how different, is any other way to do it in a more, creative way to do that. Can we identify collaboration opportunities to conduct research for the next 2 years? That's exactly the purpose for this session. We would like to build up collaboration and connection with people who have a common interest to this topic. And specifically, we will have two sessions, session A and session B, and each one will focus on different topic. And the first one will focus on the high latitude forcing, and the second one will focus on the lower ionosphere forcing. I will leave that to our co-convener, Qingyu and Astrid, to introduce each individual topic. Right? Welcome, Qingyu.
So thanks to you for the nice introduction. So this is Qingyu from NCAR. So today I'll go ahead and introduce the interhemispheric asymmetries associated with the high latitude forcing. So the high latitude forcing we are referring to this in this presentation are the ion convection, typically in a two-cell pattern, as well as the aurora particle precipitation, typically occurs in the ring-shaped region called aurora zone. So both the ion convection and aurora particle precipitation are associated with the coupling process between the magnetosphere and ionosphere, and they can be quite dynamic and intense during the geomagnetic storms. So so the high latitude forcings plays an important role in terms of the IT system variations. For example, the high latitude ion convection plays an important role in controlling the F region plasma density in the polar region. The high latitude forcing can also affect the high latitude winds through the ion-neutral coupling process. And the ion-neutral coupling process can also generate strong geoheatings during geomagnetic storm, which can affect the global IT system to a great extent. So several factors actually contribute to the interhemispheric asymmetries in high latitude forcings. First is the IMF, the interplanetary magnetic field, as well as solar wind conditions, especially when the IMF has a strong down dustward component, the BY component. And the second factor is the season. So as you mentioned, so we are actually past the June solstice. So the northern hemisphere receive more UV radiations, while the southern hemisphere receive less. So the conductance in there have the interhemispheric asymmetries, which could cause different MI coupling processes in the different hemispheres. The third factor is the magnetic field configurations. So as shown on the right, so there is an offset between the geographic geomagnetic pole, and the offsets are different in the different hemispheres. Meanwhile, the intensity of the magnetic field is different in the different hemispheres, leading to different ionospheric conductance in the different hemispheres, thus the different MI coupling process. And meanwhile, in addition, so due to the offset between the geographic and geomagnetic pole, the distributions of high latitude forcings are different in geographic coordinates in different seasons, in different hemispheres. So although this presentation mainly focuses on the large scale, the interhemispheric asymmetry could also occur in the small and mesoscale structures. So for example, the intensity of small scale and mesoscale forcings significantly depend on the season. So it could be, so a large interhemispheric asymmetries could be expected during the solstice. So, however, so we have one talk for focusing on the small and mesoscale forcings, the interhemispheric asymmetries in the small and mesoscale forcings. However, it's still more efforts are still needed to figure out to understand the interhemispheric asymmetries in high latitude forcings on different scales as well as causes. So if we put the seasonal effect aside, so the high latitude forcings can still be the high latitude IT system can still be quite different in terms of, for example, the neutral wind as well as the electron density. So however, those studies are just mechanism study or statistical studies, and more effort. So the interhemispheric asymmetries in the in the high latitude IT system are still need to be studied in depth. So the asymmetries. So the asymmetries in the high latitude forcings also contribute asymmetries in the geoheating. So as you can see on the right, so the high latitude forcings are quite different in the different hemispheres during the storm, the 2013 St. Patrick's Day storm. And the high latitude forcings is derived from the data assimilation technique, the AMI technique. So you can see there is a not very large the interhemispheric asymmetries in the high latitude forcings. So the high latitude forcings contribute to, so the geoheating heats up the neutrals, and thus the interhemispheric asymmetries and geoheating also may contribute to the interhemispheric asymmetries in the neutral density. So the geoheating can also trigger the traveling atmospheric disturbances, the interhemispheric asymmetries in the geoheating may contribute to the different generation, propagation, and interactions of TIDAS. And during the 2017 St. Patrick's Day event, the TIDAS can contribute to the asymmetric ionospheric response at low and middle latitudes through the transport process associated with the neutral winds. So the thermosphere composition can also be affected by the geoheating. So the interhemispheric asymmetries in the geoheating can also contribute to the interhemispheric asymmetries in the thermosphere compositions. That's the ionospheric electron density. So we also have one or two related talks about the interhemispheric asymmetries in the thermosphere compositions in the morning session, as well as their consequence in the ionospheric in terms of the ionospheric electron density. However, a more comprehensive understanding on the interhemispheric asymmetries in the geoheating to the interhemispheric asymmetries in the global IT system is still needed. So, if the seasonal effect is important, the high latitude the interhemispheric asymmetries in the high latitude system in the global IT system may be more complicated due to the interhemispheric asymmetries may not only contribute by the interhemispheric asymmetries in the high latitude forcings. So therefore, so as you can see in the figure here, even the high latitude forcings are identical in the both hemispheres, and a dipole tilted geomagnetic field is used. The high latitude IT system can be still quite dramatically different in the different hemispheres due to the seasonal effect. So then the cautions are needed when we interpreting the interhemispheric asymmetries occurred during the solstice to the interhemispheric asymmetries in the high latitude forcings. So there are a lot of misses, and there are a lot of myths in terms of the interhemispheric asymmetries globally. So, for example, this morning session tried to understand and identify and understand the interhemispheric asymmetries in the high latitude forcings. For example, what are the interhemispheric asymmetries in high latitude forcings and energy input, and what are their causes? And meanwhile, we also this morning session also try to improve try to focus on the improving the capabilities and of how the GCMs or other models can capture the interhemispheric asymmetries in high latitude forcings. Second, So this morning session also try to understand, identify and understand the interhemispheric asymmetries in the global IT system, particularly the causes related to the highlighted forcings asymmetry. So we also try to identify the challenges to achieve the first two goals, as well as the potential pathway to address those challenges. So this morning session probably the afternoon session also try to facilitate facilitate a robust collaborations between the observation part and the modeling part. And you will hear a lot of ongoing processes regarding the interhemispheric asymmetries in the morning session. So with that, I'll stop here, and thank you for your time, and see you soon.
Good morning, everybody. So after Qingyu talked about the influence from the high latitude on the asymmetries, I will now talk a little bit about how the lower atmosphere can contribute to asymmetries in the upper atmosphere. And I mean, you already made the point that we have to be careful about what we mean by asymmetries with respect to what is it same geographic location, magnetic location, same magnetic field strengths, and so on. So we just have to be aware of that. You mentioned this, and also Qingyu, because that's an important point. We have seasons due to the tilt of the Earth, and this will lead to differences in the background atmosphere, also in the lower atmosphere, and among others, this will change wave excitation in the lower atmosphere, which then propagate up. So this is an important point. The other is that the Earth is further away in around July from the sun than in January, and we can see these effects, for example, in the plasma distribution. So there is an annual variation in the upper atmosphere. This is very basic. It's the zonal and diurnal mean temperature. And on the left side here, this is local summer. Here is local winter. And it shows you the mean temperature. So here you have warming, and the arrows kind of indicate in a schematic way that this will affect the mean circulation. So you have some upwelling and then poleward turning of winds. Here, so this is solar absorption by water vapor here, while here in the stratosphere, it's absorbed by ozone. So if you have any differences in the distribution of ozone, this will affect the heating. So here in the summer, you have solar radiation, while this is in darkness here in winter. So you get this increase in temperature, an upwelling of the wind, this mean circulation. With the upwelling, you get adiabatic cooling. In addition, then waves are propagating up, and they are influenced by the background atmosphere. So the coldest place on Earth is the summer mesopause here. So you have the summer to winter circulation here. So in addition to this, the energetics here, you also have the waves generated by the absorption of solar radiation. Here in the tropics, latent heat release can generate tides. So these are global scale waves with harmonics of the solar day. You can have planetary waves. These are large scale waves with periods of 2 to 20 days, normal modes of the atmosphere. But you also have these smaller scale waves like due to, for example, wind blowing over mountain ranges. You have the Rockies, for example. And topography of Earth is not symmetric with respect to north and south, and it's not equally distributed in longitude. So you can get these gravity hotspots, and you also have jets, and there can be shears, and then generating gravity waves. So they can propagate up, they can dissipate depending on the background conditions, put their momentum into the mean flow, which then can influence the propagation of other waves. And then also waves can be modulated by the background atmosphere. So if you have one wave dissipating, for example, a planetary wave with 3-day period, you might see this then in tides as well in the upper atmosphere. There's also wave-wave interaction. So it's a very complex system which we want to understand. And I think CEDAR is kind of a community where we can connect with experts of this lower atmosphere to really understand what we see much higher up. I like this schematic here from William Ward and colleagues, kind of highlighting that it's a very complex connection. So you have the energetics here. If you have, for example, some heating, this will influence the wind. When you influence the wind, this will change the background condition and the waves which propagate through it. Then this is also changing the mean, or can change the mean circulation, which then can influence your composition. And if you change the composition distribution, for example, ozone, this can then feed back through absorption of solar radiation to the thermal structure and so on. So it's very complex. Here are a few examples, and probably you heard about this, the polar vortex, so in the stratosphere. In the southern hemisphere, shown here is potential vorticity in the colors. You see it's deep red here in the winter hemisphere in the south. So the polar vortex is very stable. That's it's generated basically because you have heating at the equator, but the winter pole is in darkness, so you get a huge temperature gradient, and that's why you get this vortex. So it's stable here, but in the northern hemisphere, you can see it's much weaker, and it's also distorted. And one effect which the CEDAR community has studied quite a bit is then sudden stratospheric warmings, so where this vortex shifts off the geographic pole, and then sometimes it breaks up into two, and you get these huge planetary wave effects and a heating associated with it, and changes in the mean wind. So it's much more common in the northern hemisphere than in the southern hemisphere. But there was a rare event here in September 2019 of a southern stratospheric warming. And here, this is from Larissa Goncharenko and colleagues' result, studying if a southern stratospheric warming has similar effects than a northern stratospheric warming event, showing the differences in TEC. So this is around 5 TEC units here. So there are strong effects also from southern stratospheric warming. And she will give a talk in the afternoon session. Already mentioned this. I think that the temperature in the polar mesopause in the north is colder than in the south. This is shown here from data. This is the difference between the south and the north here. And this has implication. I mean, this is probably due to different backgrounds, and that gravity waves are filtered differently. And you can see this in noctilucent clouds. So these are these beautiful clouds with ice particles in the mesosphere. And since it's colder in the winter in the northern mesopause, you can see these clouds much more frequently. And this is shown here. This is the occurrence frequency. So it's much larger in the northern winter than in the southern winter. And it also extends more equatorward. And this is an indication that the background atmosphere is different, and this will also influence other waves. There are also differences in large-scale waves. Here's an example this is semidiurnal tide. Observations over a whole year. This is winter, this is summer, winter, and this is in kind of at the same latitude in the southern hemisphere. And shown is the amplitude here in the zonal wind. You can see the amplitude is much larger here in the north than in the south. In addition, the transition from summer to local winter here has this feature of a secondary peak, which is totally missing in the southern hemisphere. So it's not symmetric. I included this one here, although this is from Maute, and the instrument mainly observes the northern hemisphere from -10 to 40. But I wanted to highlight here, this is in the E region, the wind of the migrating semidiurnal tide. And you can see the peak at mid-latitude over day of the year here. So what we are used to, that it peaks here, this is in the F region. And you can see the structure is very different. There's no peak here, it's actually a minimum. And this indicates that there must be some in situ forcing or some nonlinear interaction or eye-neutral coupling, and whatever is going on can lead to some asymmetry. So not everything is just propagating up. I mean, it also depends on what is happening in between. Lastly, I want to make the point which already Yue and Qingyu made, but now also for the low latitude, that the magnetic field is very important, not only for magnetosphere-ionosphere coupling, but also for the low latitude. And so it's not only the strengths, so here is the strength of the magnetic field, which varies with location. It's also the distortion, and the distortion is not uniform with latitude, or it's not even the same at different conjugate points. So you have to be aware of this. And in addition, the magnetic field is changing with time. And it's not a uniform change. So in some regions, it's changing much faster than in others. While, I mean, it's not changing from day to day, but I think on a year basis, maybe we should pay more attention. For example, here in the South Atlantic, it's rapidly changing. So for the electrodynamics, we often assume large spatial and temporal scales. And so the electric field at conjugate points is the same if you consider that. But if you now calculate, for example, the E-cross speed drift, the derivatives will be different. And since the magnetic field plays a role there, you will have different drifts in the two hemispheres. And indicated here is you can also have different influences from the neutral wind. If you have a declination of a field line in one direction, it can push the plasma up. But if it goes in the other direction, it can push the plasma actually down. And the same is with the inclination and mainly the meridional wind. And you can have also different illuminations at different foot points or along the field line in the two hemispheres. So it's a very interesting system, and I think these effects play a significant role at dawn and dusk. So I invite you to the afternoon session to hear from experts here to get the conversation going, how we can make progress and better understand the whole system. And I end here.
Our next topic here is another science highlight on insights from the NSF FIREBIRD 2 CubeSats into energetic electron precipitation by Katharine Duderstadt.
Hello, I'm very pleased to be here to present a summary of work that was done and supported by the NSF CEDAR program, led by teams at the University of New Hampshire and NCAR. Our work was inspired by the launch of the NASA Van Allen probes satellites that travel through the radiation belts, as well as the student-built NSF FIREBIRD CubeSats that are in low polar Earth orbit. So we were asking, can these new observations help us better quantify energetic electron precipitation into the atmosphere, primarily from the outer radiation belt, as well as to better understand the effects that this electron precipitation have on the ionization and composition of our atmosphere. We're primarily interested in altitudes below 90 kilometers, so that's the mesosphere and the upper stratosphere, involving D region ionospheric chemistry, at geomagnetic latitudes of about 55 to 70 degrees. So when these electrons precipitate into the atmosphere, they ionize the atmosphere and enhance odd hydrogen and reactive odd nitrogen, which leads to the catalytic destruction of ozone. This is particularly important in polar winter when the air masses cool and descend into the stratosphere. So ozone absorbs and re-emits energy and therefore affects the temperature of the background atmosphere, modifies photochemistry, and can influence atmospheric dynamics, such as the atmospheric waves that Astrid was describing. So the question was, what can we learn from these new observations? The NASA Van Allen probes were orbiting from 2012 to 2019, providing near continuous observations within the radiation belts. The student-built FIREBIRD 2 CubeSats were launched in 2015, and one of the CubeSats is still providing data. And these really give 3 to 4 minute snapshots of precipitating electrons, just at the top of the atmosphere. So the question was, how can we use these two platforms to better quantify electron precipitation into the atmosphere? And also, global climate models are continuing to improve. So our question was, how can models like the Community Earth System model or the whole atmosphere version, the whole atmosphere community climate model, WACCM, help us better understand the effects of electron precipitation in the atmosphere? So I wanted to mention that one of the results of this project is that WACCM now has the capacity to directly read in electron precipitation files at the top of the atmosphere. So if you can provide a differential flux file, WACCM can then itself calculate the ionization within its atmospheric simulations, and then from there predict the chemical composition changes. So if you're interested, I encourage you to contact Dan Marsh at NCAR. He has developed a Jupyter notebook code that can help take observations and put them into an input file that WACCM can then read for simulations. So this is really a great tool for our community. So the primary methods that we used were involving a conjunction study, so looking at conjunctions between the Van Allen probes and FIREBIRD satellites to try to understand what percentage of electrons that were seen by the Van Allen probes ECT instruments at pitch angles that were very close to the loss cone actually likely precipitate into the atmosphere based on the observations that we had of the FIREBIRD CubeSats near the top of the atmosphere. And so we looked at the flux ratios during these conjunctions and conducted a statistical study of these flux ratios as a function of energy. For our current model simulations, we really focus on the median of the statistical study, just to get an idea of how much of these electrons that are observed within the outer radiation belt are likely precipitating into the atmosphere, and use that electron flux to drive our model simulations. So this is an example of an electron precipitation map that we're using to drive our simulations. This is for October 29th of 2016 and shows the electron flux as a function of both energy and L-shell. And here is an example of our full data set where we take the full Van Allen probe's RBSP ECD electron flux from 2013 to 2019, and then we scale it according to our statistical study of the FIREBIRD Van Allen probes ratios, and create these precipitation maps at the top of the atmosphere. This particular one is for L-shell 5, and we're currently trying to find the best way to interpolate the missing data points so that we can get this full input map to drive our WACM simulations. Very excited to see what this will give us in terms of the effects of electron precipitation on our atmosphere. So what's really unique about these FIREBIRD CubeSats and the Van Allen probes are the energies of electrons that they're measuring. And so they measure a differential energy flux at the energies that are really significant to the middle atmosphere. This helps us determine the spectral shape of the electrons that are precipitating into the atmosphere. I'll note also that the instrument geometry of FIREBIRD is really great to provide very good sensitivity during times of quiet and moderate activity. Most of the electron precipitation estimates that are currently being used in the global atmospheric models come from the NOAA POSE satellites and the European MET-OP satellites. And these provide excellent coverage and over both spatial and temporal times. However, their energy resolution is lower, and they observe integral energy channels as opposed to differential energies. So as an example, the most recent coupled model intercomparison project, or CMIP-6, is now including energetic particle precipitation and uses a parameterization that's based on these POSE satellites using the MEPET instrument's 0-degree telescope. The MEPET instruments have both a 0-degree telescope and a 90-degree telescope, and depending on what latitude you're at, one of these telescopes is either, in the lost cone or measuring trapped electrons. And so as I mentioned, the current models generally, the CMIP-6 models generally use this 0-degree telescope, which is known to underestimate electron precipitation. So our studies, which have primarily been case studies of events to date, are showing that when we put in these energies that are important to the middle atmosphere, we are seeing ionization and enhancements of nitrogen oxides at lower altitudes than the current CMIP-6 simulations. And of course, this is important because this means that there is also enhanced ozone reductions, more ozone reductions in the stratosphere than the CMIP-6 simulations might be predicting. So continuing on with this idea that the FIREBIRD CubeSats were student-built, we also had some student engagement with our work, and in particular by undergraduate students, which was just phenomenal. So Isabella Householder joined our group when she was a freshman and remained through her junior year, and was looking at a comparison of the FIREBIRD electron flux with what Pose was seeing. And so what she did essentially was identify when conjunctions were to occur between the FIREBIRD CubeSats and the Pose and MEDOP satellites, and then targeted download of high-resolution data from FIREBIRD during those times, took the FIREBIRD electron flux, and then calculated the equivalent counts that the Pose MEPED instruments would see based on their instrument geometry in order to compare. So this figure shows the equivalent counts that Pose should see based on the FIREBIRD data and compares it to what Pose actually does see with the MEPED 0-degree telescope and the 90-degree telescope. Once again, the 0-degree telescope at these higher latitudes is likely within the loss cone, but not capturing everything, and so therefore probably under-predicting. And the 90-degree telescope is measuring the much higher trapped electrons. So we're taking for now the geometric mean of the two, which is a very rough estimate of what might be precipitating in the atmosphere. Based on her study of all these conjunctions, the FIREBIRD observations are generally somewhere between the 0-degree telescope and the geometric mean of Pose. And our next step is really to compare the FIREBIRD data with data sets that do a better job of combining these 0 and 90-degree Pose telescopes, which are much more complicated than just one is in the loss cone and one is in looking at trapped electrons. And Josh Pettit actually gave a poster yesterday that is hopefully still out there that you can look at that provides one of these great data sets that we're hoping to compare to. So another student research project resulted in a senior thesis of Timothy Rader at the University of New Hampshire. And he was really looking at the FIREBIRD higher energy channels, and this is low resolution 6-second data, and there's a lot more of it. And he was looking at these higher energies to see if a statistical analysis of this data could show evidence of electron precipitation during electromagnetic ion cyclotron wave events, EMIC wave events that occur in the magnetosphere and were observed by the Van Allen probe's emphasis instrument. And indeed, he did show this evidence, which was just, which was fantastic. He also demonstrated that as the solar cycle decreases, strong precipitation events at these higher energies also decrease. However, the background levels actually increase. And finally, I did want to mention that we did also conduct some Wacom-X experiments and showed some significant enhancements in electron density and conductivity at the altitudes that we were interested in. So the main conclusions of this study were that we can use the FIREBIRD CubeSats as well as Van Allen probes together to come up with a new electron precipitation data set from 2013 to 2019. And we're very excited to see what the model simulation results are from these. That the effects of radiation belt electrons in the middle atmosphere may be larger than is currently being predicted, especially by the simulations such as CMIP6. And also that we're just really pleased that NCAR now has this new tool that is able to read in directly the differential electron flux at the top of the atmosphere into the model. So a new capability of the Wacom model. However, in order to further understand electron precipitation and its effects on the atmosphere, we really need more observations that assess the pitch angle dependence of these precipitating electrons at the top of the atmosphere. This was one of the largest challenges, is to determine actually what's coming into the loss cone. I will note that there are a couple of reviewed articles that are recent that do a really great job of providing the background of what studies have been done on this and where we're heading in the future. We also, would like to recommend that there be more instruments such as FIREBIRD or FIRE on FIREBIRD that measure the higher resolution in the energy channels of interest to the middle atmosphere. And the APEX mission will have an instrument, AFIRE, that is very similar to FIREBIRD, so we're excited to see what data it brings back as well. It would also be great to have more studies that look at how the localized changes in ozone from the electron precipitation really do affect the atmospheric dynamics and radiative processes. And then finally, these CubeSats are invaluable for teaching students. And so from our experience, we really want to encourage research teams to include undergraduate students, even beginning as freshmen, so that you can follow them through their undergraduate experience, and the research experience can inform what they're learning in their coursework and affect their retention within fields such as physics as well. So with that, I do want to thank the CEDAR community and the NSF CEDAR program for supporting this work, and look forward to seeing it develop in the future. Thank you.
Thank you. One question for Katharine.
Could you comment on the possible importance of incoming photons and alpha particles? Could you comment on the possible importance of incoming energetic photons and alpha particles? Because I noticed you focused pretty much on electrons.
Yeah, we did focus on electrons in this study, primarily because FIREBIRD was observing electrons. So the protons and alpha particles, I've studied those previously from the sun, and so that's what I'm used to, is solar protons. They tend to penetrate more deeply into the atmosphere, affecting the lower stratospheric regions as well. So as I mentioned, our study does not include this. However, the WACM model and the CMIP-6 simulations do have protons included within their studies as well. And so as the CMIP-6 simulations come out, their protons, they discuss the protons in those articles. Yeah. All right, thank you.
Thank you, Katharine. Our last talk today for the plenary session is the Grand Challenge Report on Poynting Flux by Alex.
Okay, so I'm here to talk about the Grand Challenge we've been doing on Poynting Flux. I wanted to explain a bit why we proposed this, why I think it's a grand challenge. So in most of the estimates that we have, the Poynting Flux is the largest unknown source of energy for the upper atmosphere and ionosphere. And during a storm, it could actually be the largest term. So it could be more than EUV in a major storm. So to put it into context, in the United States, if my Google answer is right, approximately half a terawatt is used of electrical power on average. And it could be more than half a terawatt. It could be maybe even a terawatt during a major storm. It is how much energy it comes into the upper atmosphere. So we really need to get a handle on this if we're going to understand how the system works. And what I'm going to show is some interesting findings that we've got from different people. We've seen excellent progress on, for example, the asymmetry in the Poynting Flux. This is something in the last couple of years we've seen from different missions. There's more going into the northern hemisphere systematically. We've seen regionally excellent agreement. When you have really good data coverage and treated well, then people can start estimating accurately the amount of resulting joule heating and atmospheric expansion. But we also can see that there's huge differences between the different estimates, and there's an awful lot more to learn about this. So just in summary, what is Poynting Flux? I think we're going to have to go through every session we've done, and we always have these confusions because it's a little tricky mathematically, and approximations that work well in one domain don't work well in another domain. So we always go through some of that. I'm going to try to show just basic examples of how it can be important, how it can relate to other parts of the system. There are some problems which come in interpreting what the Poynting flux means in terms of other parameters when you make assumptions. And I'll just try to finish with some next steps that we need to take. So first of all, the Poynting theorem comes directly from Maxwell's equations, and in itself is hard to challenge. The typical assumption we make is that the electromagnetic energy density is a constant in the regions which we're studying, which I believe in the upper F region is usually acceptable. And in that case, then you try to relate the Poynting vector, so the E cross B over mu naught term, to J.E, the Joule dissipation. And the first mistake people make is leaping in and thinking that that's just Joule heating. And it's only Joule heating if you understand the reference frame of the neutrals. So some of it can drive a wind and some of it can drive heat, and you need to have the neutral winds in there to understand that. The second thing is, well, why is it B is mostly you think the geomagnetic field. Actually, the geomagnetic field is a scalar, so that part drops out. And what we're talking about is the delta B from field-aligned currents. So you have the electric field and the delta B from field-aligned currents. Those are the driving parts of the Poynting flux. Now, up here, further up in the acceleration region, you have Poynting flux turning into particle acceleration, so it's hard to measure. And FAST did a great job of resolving how particles are accelerated through Poynting flux. How do I go back? Then when you get down into the F region, and satellites like DMSP and SWARM and soon to be GDC, there you can make a measurement of Poynting flux where it's not turning into other forms of energy, and you can kind of rely on it. As you get lower into the current closure region, then again, it's turning into other forms of energy, and it's going to be highly structured in altitude and difficult to interpret. But in this region, you can make a good measurement. And also from remote sensing, you can use SuperDAR, and you can use other types of instruments to measure in that region. So approximately, you get this integral of the LEO Poynting flux being deposited approximately between 90 and 200. There is, of course, heating higher up than that, and especially the wave terms are not small. We can see it, especially in the higher altitudes, large amounts of energy coming in through that. So there is also a question whether it actually goes just locally or if it can flow out. But essentially, this is kind of an order of magnitude sketch. You start with Poynting flux somewhere above the acceleration region. It breaks into partially kinetic, but we think more than half remains as Poynting flux at least from the MSP. That seems to be the case. You can have drifts, you can have momentum, ionization in the E layer, and heating. And so just when we look at this kind of like geophysical kind of sketch, the Poynting flux is actually coming down in between the two current regions. It's an abstract concept, but that's sort of where it fits in the most. And then when we look into the different ways that you model it, primarily long-term statistical averages, you can have, in isolated cases, you can have better measurements. But the more we look into smaller scales, the more you actually see. So we don't really know what's the inner limit of how small you have to care about. The previous challenge they couldn't, not even the same color scale, not even the same units actually in some case. But so if you look at these different estimates, they're all very, very different. And some of them have this big focus on the cusp, and some of them have more in the morning and evening sectors. We obviously can see relationships like this more in negative BZ or southward IMF, but these are wildly different estimates. And just to illustrate, I mean, this is kind of the same, this is on the same color scale at least, but you can see, okay, northward, not much, southward, a lot. And that's kind of the state of the the statistical models. Is it mostly in the cusp? Is it mostly somewhere else? We're still seeing big differences between the different estimates that people come up with. And what that translates into is when you try to model how hot the ionosphere is, this was a result we had from Leslie LaMarche in the first year of the session, I think, even before she published it. We see this like 1,000 Kelvin bias in the temperature of the ionosphere, so 1,000 kelvins hotter than what was predicted. So that's kind of one of the reasons why it's important. But then when we think about, well, how can we predict space weather and how can we understand where the density enhancements are going to be, we've got to understand that a lot of that heating that's generating these density enhancements is coming in as Poynting flux. And if you can't predict or understand if you can't understand what energy is going in, you can't predict what's going to happen coming out. Finally, I wanted to just touch on the Richmond 2010 paper. He makes the point that if you don't know the conductivity of the ionosphere, it's really hard to say exactly how the Poynting flux is going to manifest into Joule dissipation. And he goes through theoretical kind of like conductive plate examples with different current distributions that are kind of reminiscent of the Region 1 current. And if you want to read through that, there's he I think does a great job of pulling out, well, what you think might happen from one value of Poynting flux is not the same necessarily for depending on how the conductance looks. So basically from that, in an integrated sense, you can know how much energy is going in, but you can't know specifically in one place how much energy is going to come in from the Poynting flux, unless you have the conductance. So what do we need to know? Still, how much energy is going in and coming out of the system? I still think there's maybe even an order of magnitude uncertainty there. What is the conductance? Because that's going to tell us how that energy interacts with the system. How does the suborauroral plasma, we've seen this kind of this strange phenomena like the SAPs. How is that influencing what's happening at high latitudes? And what are the dominant mechanisms then that generate irregularities as a result of this? So I think we're getting to the point where we're starting to move from a climatology to actually seeing instantaneous results that match only in localized areas. We've got a number of exciting missions coming up with E-field measurements on them. So I think that's going to be, if you have E and delta B, you can do this kind of science. And some of these MAG-ITM models are just starting to get to the point where we might be able to rely on them. So that's kind of what we've had over the last couple of years. Thank you.
Question for Alex? You want to go?
It just a show that Alex and us organized this workshop discussion, and then we have lots of, we have a notes and an open notes on a white paper writing activities on this topic. So it's on our website. The agenda for this Grand Challenge workshop, so it's on top. Please, it's open so you can edit so that we can help your activities to put forth our interest on this topic.
Thank you very much, all the speakers this morning, for giving inspiring talks. Before we go into break, 2 announcements. If students, you haven't put your posters up, please do so during this break. And second, we will have a town hall at noon, from noon to 12:45 p.m. in this ballroom on decadal survey and future of CEDAR instrumentation. So please plan to join that. We should have interesting discussions. And we can head into the break. Thank you very much.